continue. Now, so yesterday we were looking at modular arithmetic. It was just a revision. And again, today we want to do revision on linear congruence, where we'll be solving congruence equations if given to us. Now, so a congruence equation is an equation of this type. AX is congruent to B mod M. So we're supposed to find the value of X. This is what we mean by a congruence equation. Or we're supposed to find the value of X. So there are various ways of doing this. But we will begin by use of the extended Euclidean algorithm to solve this type of equations. Then later on, again, we shall see that we can solve using inverses. That is, if you know the inverse of A, then you can multiply both sides by the inverse of A, multiply both sides by the inverse of A, if you know it. And of course, we also learned how to calculate inverses. And of course, we shall also look at it again. So that if you have the inverse, you can also solve this type of equation. But I want us to begin by looking at how to solve using the Euclidean algorithm. So first, before you solve, you have to find out whether it has a solution or not. If it has a solution, you begin to solve. And if it has no solution, you say it has no solution. So that means you cannot solve. Now, so how do we tell if this equation has a solution? We look at A and M, find their GCD. Find the GCD of A and M. The GCD of A and M. If the GCD of A and M can divide B, and then we say that this linear congruence equation has a solution. And of course, we said how many solutions? The number of solutions will be equal to the GCD. The number of solutions will be equal to the GCD. So that's what I've written here. Under this note, I've said note, this equation has a solution if its GCD divides B, this B. If the GCD of A and M divides this B. So supposing the GCD is D, you're saying that that D should divide B. If that GCD divides B, then we say this system has a solution. And of course, the number of solutions will be equal to that GCD. If the GCD cannot divide B, we say it has no solution. So we're to begin looking at this example yesterday. And as I said that if the moduli is this small, we can begin by just testing elements mod 9, for instance. Elements mod 9. These are the elements mod. This is what we mean by elements mod 9. These are integers. You know, these are integers. This is a set of integers. This Z is the set of integers. Now, integers that are less than 9, that set less than 9 and greater than 0. Now, from 0 to If I'm talking about M, the elements from 0 to M minus 1, these are the elements here. So for instance, this is the same as Z8, the integers mod 8, the integers mod 8. What are these integers? These are the integers 0, 1, 2, 3, 4, 5, 6, then 7. Those are the integers we're talking about. So you can try each of them and see which one is a solution. The integers mod 10, we write it this way. Integers mod 10. And this, of course, are the integers 0, 1, all the way up to 9. So you're just trying all of them. If the moduli is this small, you can try all of them. But if the moduli is larger, and of course, we have another way, which we call the extended Euclid's algorithm, and we shall see how it works. So I just want us to try one by testing the integers mod 8, and then the rest we shall do by the extended Euclid's algorithm. So I want us to solve this congruence equation. The first thing I said is we find out the GCD of 5 and 8, and of course this is 1. This GCD is 1. And also, we can see that 1 divides 3. 1 divides 3. Therefore, this equation has one solution. So you test all of them, and I think we tested yesterday. We tested yesterday for this for this first equation. So let's test for the second equation. This first equation we tested yesterday. So the second equation, again, we find out the GCD of 6 and 10. The GCD of 6 and 10. And this looks like 2. And 2 divides 8. So the system has two solutions. So we can test. The 10 is a very small number. We test 0, 1, 2, all the way up to 9. And this, I said, we call it Z mod 10. This is how we write it, Z mod 10. These are elements 0 to 9. So let's test 0. 6 is 0. This is 0. And of course, is not the same as 8. We test 1, get 6. And of course, again, is not 8. Test 2. This is 12. Mod 10, that would be 2. 12 mod 10, that would be 2. And of course, again, this is not the same as 8. It's not congruent to 8. We test 3. This would be 18. 18 mod 10. The remainder is what we write, is 8. So this is a solution. 3 is a solution. That is one of the solutions. Let's test 4. That will be 24. Mod 10, this will be 4, which is not congruent to 8. Can test 5, and this will be 30. Yes, mod 10, this will be 0. 30 mod 10, that's 0. That's the remainder, which is not congruent to 8. What about 6? Mod 10, the remainder is what we write. 6 on division by 10, the remainder is 6, which is not congruent to 8 mod 10. So 6 is not a solution. We try 7. Have we tried all of them? Okay, 7 will be 42. I think we have skipped something. Oh, no, we are going up to 10, up to 9. It's okay. So this will be 42. Mod 10, this will be 2, which is not congruent to 8. So we try 8. 48. Mod 10, this will be 8. So that means 8 is another solution. We had said there are only 2 solutions. There's no point of proceeding. We've already obtained the 2 solutions. But let's just proceed for the sake of completion. Let's just do that. Let's test the last one. This will be 54. Mod 10, the remainder is 4, which is not congruent to 8. It is not congruent to 8 mod 10. So this is how you do it. If the moduli is small, but if it's large, I want to show another way. And I also want to try this E, just to emphasize what we said yesterday, that while working with the mod, you just work with them the same way we do with other integers. You can cross equal sign. And if the sign was plus, it changes to minus. And if it was minus, it will change to plus. You can multiply, you can divide on both sides, and so on. So there's nothing unique with the modular arithmetic. The only thing you need to remember always is that you dividing by the mod and writing the remainder at every instance. So that is the only thing that we need to recall while doing this. But every other thing, we do it just the same way we do with the normal integers. So number E, we have 6x minus 3 is congruent to 5 plus 2x mod 10. We can collect like terms as we've always done. Let's keep the unknown on the left side. So this one crosses the equal sign. It has a positive sign. When it crosses this sign, this equivalent sign here, to become minus. So this would be minus 2x. And we have this 5, but this one, let it cross and come this other side. Its sign on this side is minus. Going this other side becomes plus. So what do we have here? This is 4x is congruent to 8 mod 10. 8 mod 10. Now, so we've now simplified this. What follows next now is to solve it. But before that, we check if it has a solution. Find the GCD of 4 and 10, which is 2. And check whether 2 divides the number after the equivalent sign. Check that. Of course, 2 divides 8. Hence, has 2 solutions. Hence has 2 solutions. So you can now test, because you're doing mod 10, you can test integers from 0 to 9. From 0 to 9, and we're using this equation now. We're using this equation. Let's test 0. This gives us 0, which is not congruent to 8. Let's test 1. This gives us 4, which is not congruent to 8. Let's test 2. When you test 2, what you get is 8. But of course, this is what we wanted, mod 10. So the first solution, therefore, is that our x is 2. Our x is 2. So I want to look for the other remaining solution, because from the start, we saw that it will have 2 solutions. So the first solution we found is 2. We test 3. This is 2, which is not congruent to 8. We test 4. And if you test 4, this will be 6, which is not congruent to 8. We test 5. This will be 0, which is not congruent to 8. Mod 10. We test 6. This will be 4, which is not congruent to 8. Mod 10. We are going up to 9. You test 7. This will be 8. Mod 10. So the other solution, therefore, is 7. So because we knew that the 2 solutions and we found them, we see no need of proceeding to look for others, because what are we looking for? You've already have the 2 solutions, unless if you want just to show that the remaining ones are not solutions. Unless if that is the case, then we can proceed to prove that 8, which will give us that 2, which is 2, is not congruent to 8 mod 10. We also prove that 9, which is 6, is not congruent to 8 mod 10. So that's how we do it, using our trial. And of course, we emphasized that this it's trying for you numbers from 0 to m minus 1. That can happen. Now, any question before I look at now how to use the extended Euclid's algorithm? Any question? Okay, I cannot see any on the charts. Anybody with a question? Okay, let's look at how to use the extended Euclid's algorithm. Now I'll do the same questions that we've done before, these ones, to show the extended Euclid's algorithm before I proceed to the others, larger, the ones with the larger moduli. So I begin with this ones with the small moduli. Of course, our procedure is the same thing. Whichever method you're using, The procedure is the same thing. The first thing, find the GCD. And the second thing, find out whether that GCD divides the number before the mod. Then use the extended Euclid algorithm. Now let's do this part A. Let's do this part A. I'm now using the extended Euclid algorithm. The first thing, my solution, I will find the GCD of 5 and 8, which is 1. And check whether 1 divides 3. Of course, it divides 3. Hence, the equation has one solution, because we said the number of solutions are equal to the GCD. Since we've confirmed that it has a solution, we can now begin using the Euclid algorithm, and we're using this number and this. The ones we use to get the GCD are the ones we are using. It's 2. We are using the Euclidean algorithm, then the extended Euclidean algorithm. So as we normally do it, what is 8 divided by 5? 8 divided by 5, 5 will go there once, and the remainder will be 3. What about 3 into 5? 3 into 5, it's ones, and the remainder is 2. What about 2 into 3? 2 into 3, it will be ones, and the remainder will be 1. So let's just do it until we have a 0 remainder. 1 into 2 will be twice, and the remainder is 0. So I've decided to write the number of times it goes on my left. Then this sign, this dot here is multiplication. This dot here is multiplication. So this one means 1 times 5 plus 3 will give me 8. 1 times 5 plus 3 gives me 8. 1 times 3 plus 2 gives me 5, and so on. Now, so having done this, this number, the remainder here, just before the remainder of 0, the remainder just before the remainder of 0 is the GCD. And you can see we had already said that GCD is 1. So once you find that this is a GCD, you make it the subject of the formula. You make this GCD the subject of the formula, and then replace this remainder as going up. Replace this remainder as going up. So we begin with this first remainder, which is our GCD. This last remainder here, which is our GCD. We write it in terms of these 2 other numbers. So to write it in terms of these 2 other numbers implies taking this other number to this side of the equal sign. Take this number to this side of the equal sign. So that means 1 equals 3 minus 1 multiplied by 2. Now replace the next remainder. We are done with this remainder here. The other remainder was this, which is here. Replace it. So this will be the same as 3 minus 1 multiplied by 1 multiplied by this remainder 2. What is it in terms of these other 2 numbers? What is this 2 in terms of these other 2 numbers? It's the same as 5 minus 1 multiplied by 3. What does this give us? This is 3, this 3. I now expand, multiply by this minus 1 inside the bracket. And I make sure I don't touch this 3 here, because it's our next remainder to be replaced. It's our next remainder to be replaced. So what I do, this 3 I've written it. This -1 times 5, what I get is -1 times 5. Then this -1 times this -1, what I get is +1. Then there's a times 3 there. Now collect like terms. And the like terms are the ones that have a 3. The ones with a 3. But let me first of all even write this other one, which is -1 multiplied by 5. Now, the ones which have a 3, if you were to factorize, what you would then get would be 2 multiplied by 3. If you were to factorize, how do we factorize? You see, this is just 3 plus 1 multiplied by 3. So what do we do? Suppose I was to write 3 here. I would ask myself 3 into this how many times? 1. Then there's a plus sign here. Then 3 into this, 1. So that's how I get this 2. That's how we factorize. Now, so the next thing, therefore, is to replace this other remainder. Replace this other remainder, 3, which is here. Replace it. So what do we get? Let me write this one first. Then plus 2. Instead of 3, we write the equivalent. The equivalent, just taking it on the other side of the equal sign, be 8 minus 1 multiplied by 5. I remember when I was doing this, I was using brackets, but there's no problem. The thing is, you're supposed to see what is happening. Supposed to see what is happening and follow. Now open the bracket using these 2. Open the bracket. But before that, you have to write this, which is -1.5, not times 5. 1 times 5, -1 times 5. Then this other will be plus 2 times 8. 2 times 8. Then this other one will be minus 2 times 5. 2 times 5. Remember the dot there is just times. The other time we're using brackets. It's the same thing. Correct like terms. The one that has that have 5, we have -3 times 5. Then plus 2 times 8. What was the question? Well, to find the value of what is multiplied by 5 to get 3. Now what do we have? What we have is what is multiplied by 5 to get 1. What we have is what is multiplied by 5 to get 1. Let me just erase here. That I show you what we are doing here. So it's good to know what we want. Because what we want in this question is what is it that when multiplied by 5 gives you 3. What do we have? What we have is this. What we've just obtained is this. -3 times 5 plus 2 times 8. In fact, what we have is that -3 multiplied by 5 gives me 1. Let me call this equation x. Call this equation x. I want a 3, but I have a 1. So that means I multiply this x, multiply x by 3. So when I multiply x by 3, at this point, you have a 3. This other point, you have negative 9 times 5. And at this other point, you have a 6 times 8. What I'm interested in is what is multiplied by 5. This point. I can see from here that x is negative 9. That is what is multiplied by 5 mod 8. And this we did yesterday, dividing this into that. We just say, how many times does 8? Supposing the 9 has no negative. How many times would 8 go into 9? Go there 1 point. So we take the number, whole number larger than 1 point something. The next whole number will be 2 and give it a negative sign. So that means 8 will go into negative 9, negative 2 times. So 8 will go into negative 9, negative 2 times. And negative 2 times, that will give you negative 16. And when you subtract, you have a 7. So this is same as 7 mod 8. That is the same answer we had gotten by trying. That is the same answer we had gotten by trying. So those are the steps. We just used the Euclid's algorithm, and then extended Euclid's. This is the Euclid's algorithm, this one. This one is the Euclid's algorithm, where you're dividing by 5, and you say it goes there 1, and the remainder is 3. Then you ask yourself, what about 3 into 5? Goes there once, and the remainder is 2. What about 2 into 3? This is the Euclid's algorithm. Then this is the extended Euclid's algorithm, where now you're making the GCD the subject of the formula and writing that GCD in terms of 5 and 8. So you can see we wrote the GCD in terms of, in fact, we wrote it here. We wrote the GCD in terms of 5 and 8. I can take another example, this B. I can take this B, and then we go to bigger moduli and look at 1 or 2 examples. Any question? Anywhere somebody requires clarification? Now, I chose this. It's just the same as this. The way you do it, just the same way you do it. I've chosen that because I can see that the GCD of 6 and 9 is 3. And they're different. Because the GCD of 6 and 9 they're different. Back to this one. Did we do it earlier and we got something different? Which one did we do? Did we do this? I don't remember the one we did. Because I am seeing this is 4. And this GCD is 3. It's not 2. I think we did this one. Eh? Okay, so this one.
I think it was E.
E.
Yeah.
Oh yeah, and the D. No, not D. It was E.
And I think it was E and A.
Oh, so we didn't do this B.
No, we didn't do B.
Okay. Yes, because this B, I was wondering what we did and found, because I'm seeing the GCD is 3, and I'm seeing that 3 cannot divide 4, hence it has no solution. Has no solution. This one you cannot find a solution to it, because the GCD cannot divide this number. I was wondering whether we did not see that, but it's good that we did not do it. Now let's now do C. We've seen that B has no solution, and we have the reason to that the GCD cannot divide 4. So now let's take this C. The GCD of 6 and 10 is 2, and 2 divides 8, hence has 2 solutions. Now you see, for this one, it's easier to say the GCD. It's easier to see that the GCD is 2. Otherwise, if it were larger numbers, you would begin by, first of all, the Euclid's algorithm to assist you find the GCD. After finding that GCD, now say whether it divides or not, and whether it has solutions or not. But for this smaller one, I can just see the GCD is 2. So from the very start, I can ask myself whether I should proceed or not. So this one, I think we should proceed because it has solutions, and there are 2. Now, if you are to use the extended Euclid's algorithm, and you find that the GCD is 2 or 3 or 4 or 5, and you find also that that GCD divides a number here. So it means that GCD is common to the 3 numbers. That GCD now is common to the 3 numbers. So what then that means, you divide this equation by that GCD first of all. So let's call this equation 1. So divide equation 1 by the GCD, which is 2. So when you divide it by that, what you then get would be 3 is congruent to 4 mod 5. And of course, I don't need to test whether it has a solution or not, because our original equation already has a solution. So we only want to use this to solve the original equation. So I want to call this equation 2. And now use the Euclid's algorithm, 5 and 3. 3 goes into 5 once, and the remainder is 2. 2 goes into 3 once, and the remainder is 1. You may want to proceed and say, what about 1 into 2? To be twice, and the remainder will be 0. And we said the number here is the GCD of equation 2. We make it the subject of the formula. Now what we are using is the extended Euclid's algorithm. Extended Euclid's algorithm is the one I want us to use now to make the GCD the subject. So 1, taking this part, the left side, will be 3 minus 1 times 2. Replace this 2 here. What you have is 3 minus 1 multiplied by, instead of 2, this is 2. Instead of 2, we have the equivalent, which is 5 minus 1 times 3. And so what does this become? 3, opening the brackets, you have -1 multiplied by 5. Then this, the negative times that will be plus 1 multiplied by 3. Just a minute. Okay. Now, so at this point, you collect like terms. And the like terms that we have, the one that are 3, again, when you factorize this, you would get 2 times 3. And this other one would be -1.5, not times 5. We've replaced, we have replaced all the remainders. We began with making one the subject of the formula, then replaced the 2 here. So this is then what we have. But what do we have? What do we have? We have this is equals to 1. So what we have is 1 is equal to 2 times 3 minus 1 times 5. Let's go back to equation 2 and look what we wanted to achieve. Equation 2, oh, there was an x here. There was an x there. So equation 2, what we want to achieve, wanted to get a number which, when multiplied by 3, would give us 4. Wanted to get a number which, when multiplied by 3, that number we call it x. So wanted to find an x which, when multiplied by 3, would give us 4. What we have is an x which, when multiplied by 3, gives us 1. We have an x which, when multiplied by 3, gives us 1. So, but we want the one that gives us 4. So it means you have to multiply, and I want to call this equation star. You have to multiply equation star by 4. You have to multiply it by 4. So when you multiply by 4, you have 4 is equals to 8 times 3 minus 4 times 5. What do we now have? We have an x, or a number, which multiplied by 3 gives us a 4. That's what we wanted. Wanted a number which multiplied by 3 would give us as 4. That is what we have. We have a number which, when multiplied by 3, gives us 4. Let us remember the mod. The mod is here. Let us remember the mod. So what we've now found, let me now write what we found. We found that x is 8 mod 5. But 8 is bigger than 5. So then we can say x is 3 mod 5. I've just written the remainder. On division by 5, the remainder is 3. This is our first solution. To get our second solution, so let me call it x1. Also, from the start, we knew that we are going to get two solutions from the start. So what about our second equation? It will be our first equation, our first solution, plus the mod, was 8. This time, we remember our original equation, the mod was 10. So what are our solutions therefore? Our solution, the first solution is 3. The second solution is 8. And those are the same solutions we got when we used trial. Those are the same solutions. Want to proceed to those equations with larger moduli. Unless there's a question here so that we move there together. We move to larger moduli when we already understood this. Is there any question? It's good always to seek clarification if you discover that at some point you did not get some point clearly. It's good always to seek clarification so that we proceed together. There's no question on the chat. Okay, let's proceed now to larger moduli. And to begin with this, find the least positive integer x for which I've used the word least because we know that, for instance, yesterday we talked of that question we talked about is that question we were trying to solve yesterday, and we were saying that which numbers would be congruent to 3 mod 7, for instance. We found that there were so many numbers. So this question wants the list of them all. And of course, it goes further and says positive, because the question knows that we even have other numbers which are negative and will satisfy this equation. We have others which are negative and will satisfy that equation. But now we just want the least positive. So like yesterday, this question, we say, how are we going to do it? We said numbers, this is the same as number A is congruent to 3 mod 7. So you're asking yourselves, what could this be A? And we say this A could be any number such that we said A divided by 7 gives us T, and the remainder is 3. So we wrote A as 7T plus 3. So then we said T here could be any integer, could be any integers. T could be any integer. That means if T is 0, we're finding this to be 3. If T is 1, this will be 10. If T is 2, this will be 17. So there are so many numbers that will satisfy this equation. There are so many numbers. So A can be any of these numbers, but now the question wants the least and the positive, because we know that T can also be negative. If T is -1, for instance, If t is -1, then a will be -4. So there are so many, x here can be any value. We want the list of them all, which is positive. That's why every time we are doing that, we are trying to convert it to positive, because we know that the remainder then is supposed to be positive. And the way I look at this question again, you see, when you look at this question, you're supposed to know what the question is saying. This question, I can interpret it two ways. The first way, I can interpret it, that I want to find the inverse of 53. Because I know that the inverse of 53 times 53 is what will give me 1. So that is why I said we have various methods of doing this question. So if you understood this question that way, then you can use methods of finding inverse. And we have several methods. Because what I'm seeing two numbers on the left side, which are multiplied to give us 1. And I know that the only time you get a product of 1 is when two numbers, which are inverses of each other, are multiplied. When numbers which are inverses of each other are multiplied is when we get 1. It means this x must be the inverse of 53. So that is one way I can interpret this. And the other way, if I don't know how to interpret that, is I just check the GCD of this and that, and to see what it is and see what it divides this, and begin by the Euclid's algorithm. Now let me use the Euclid's algorithm. What have we said? We've said that for you to begin doing this question, find the GCD of the two numbers, which is 53 and 93, and of course this is 1. Check whether this GCD divides the number here. And I've seen that 1 divides 1. Hence, the number of solutions are equal to the GCD. The number of solutions are equal to the GCD. So hence it has one solution. After that, use the Euclid's algorithm. 53 and 93. How many times does 53 go into 93? And you'll find that 53 goes into 93. Let me use this. 53 goes into 93 once, and the remainder is 40. 40, this one is not writing properly here. Just move it a bit. 53 there, 40, the remainder. 40 into 53, and I have that it goes there once, and the remainder is 13. So this is 1 times 40. Then 13 into 40 goes there 3 times, and the remainder will be 1. Once I reach 1, I know it will be the GCD, of course. Because I know the next stage is just to write how many times does that 1 go into 13. Go there 13 times, and the remainder will be 0. So this is the GCD. So we make the GCD the subject of the formula. What now we use extended, we now use the extended Euclidean algorithm. Extended Euclid's algorithm. You can call it extended Euclidean algorithm or just extended Euclid's algorithm, and they mean the same thing. Make one the subject, our GCD, beginning from here and moving upwards as you replace the remainders. The first remainder is 1, which is our GCD. Take this, the other side of the equal sign. You have 40 minus 3 multiplied by 13, which is 40 minus 3 multiplied by, replace 13 is our next remainder. 13 is our next remainder. What is it equal to? Check this, the other side of the equal sign. 53 minus 1 multiplied by 40. 1 multiplied by 40. Close the bracket. This will be the same as 40. Now open this bracket. You have 3 multiplied by 53. And then minus times minus, positive 3 multiplied by 40. Let's put the ones that are 40 together. That gives you 4 multiplied by 40 minus 3 multiplied by 53. Replace the next remainder, which is 40. So this will be the same as 4 multiplied by, instead of 40, the equivalent is 93 minus 1 multiplied by 53. Then minus 3 multiplied by 53. Opening this bracket here, will be 4 times 93. Remember this is 1 here, not 7. Minus 4 multiplied by 53. Just multiplying, just opening this remainder by 4, which is outside the bracket. Then minus 3 times 53. At this point, the like terms together. 4 times 93 minus 7 times 53. Where did you want? What did you want? We wanted a number which, when multiplied by 53, will give us 1. Let's write what we have. What we have is this, because we replaced all our remainders. So what we have is this is equals to that. What we have is that 1 is the same as 4 times 93. It's not writing here. Let's move it. What we have is that 1 is the same as 4 times 93 minus, minus 7 times 53. So what did you want actually? We wanted a number which multiplied by 53 gives us 1. 53 is here. The number that is multiplied by it is negative 7. So we've just found that it's negative 7 is our x. Just found that as negative 7 is our x mod 93. Mod 93. But now that is negative. To make it positive, there are 2 ways I've shown you how to do it. 1, add this number to that, and you get 86. That's one way I've shown you. Let's add this number to that, get 86. The other way I've shown you, just divide 93 to negative 7. And at this point now, you know to divide these numbers. and realize that because they are negative 1 times, negative 1 times that will be negative 93. When you subtract negative 7 minus 93, this becomes positive. You get 86. So 86 is the answer they are looking for. It's that number which, when multiplied by 53 and then divided by 93, the remainder will be 1. 86 is that number. So, of course, let me show you again the working, the typed working. Let me just erase this. There you have the typed working for the sake of recording, that at your own time later, you can look at it and follow. Then it continues, the working continues. The only problem is that, okay, at this point, this one I placed at the very margin. I place at the very margin, so it's something not clear here. Let's find out what it is. This point here, let's just write it here. It comes from here, it comes from this point, it comes from here. What was happening at this point? This point, we wrote negative 53 multiplied by 3. Then we were opening the bracket using the 4 outside, and that 4 would be 93 multiplied by that 4, and then negative 53 multiplied by that 4. I think what is missing is the 4. What is missing here is that 4. Yeah, it's okay. Then from here, we now collect like terms, and we began by writing this term here. Began by writing this term, which is 93 multiplied by 4. And then collect like terms here. Negative 4 plus negative 3 will give us negative 7. And then multiply by 53. Yes, I think that is, this one was at the end of the margin. So we've now written it properly. Let's look at this other example. Now this one, we are not looking for the inverse actually, because this is not 1. This is not 1, so we're not looking for the inverse of 7. But we're looking for a number which, when multiplied by 7, will give us 13 on a division by 19. That number, in fact, the same thing as a number which, when multiplied by 7 and then divided by 19, will give you a remainder of 13. That's the number you're looking for. But before we look for it, let's first of all see the GCD of 7 and 19. And this is just 1. And 1 divides 13. Therefore, this equation has solutions. No, has a solution. This equation has a solution, just 1, because it's GCD this one. After confirming that, we use the Euclid's algorithm first. How many times does 7 go into 19? 7 into 19, let me just do it here. 7 into 19, it's twice. Because of 14, and the remainder will be 5. What about 5 into 7? Once. and the remainder will be 2. What about 2 into 5? Twice, and the remainder will be 1. What about 1 into 2? Twice, and the remainder is 0. We have, what we've done, we've used the Euclidean algorithm or the Euclid's algorithm. From that point, we, after noticing that this is a GCD, we now apply the extended, and I'm just emphasizing so that you get the difference between the Euclid's algorithm and the extended Euclid's algorithm. They're not the same thing. Extended Euclid's algorithm, they're different. The Euclid's algorithm just uses division, a successive division. And the Euclidean algorithm is now the process of making the GCD the subject of the formula, and then writing that GCD in terms of the numbers, 7 and 19 for this case. So what is 1? Take this the other side of the equal sign. It will be 5 minus 2 multiplied by 2. Replace these 2 by these 2. So this will be 5 minus 2 multiplied by, what is this 2? This 2 is this 5 minus 7 minus that. When you take this on the other side of the equal sign, 7 minus 1 multiplied by 5. So this then gives us 5 minus 2 multiplied by 7. Minus times minus, positive 2 multiplied by 5. Collect like terms. I want to collect it. You can just collect it anywhere, either on the left or, let me just collect it here. With 3 multiplied by 5 minus 2 multiplied by 7. Replace now the last remainder. The last remainder. 3, that last remainder is here, 5. It's equivalent to 19 minus 2 multiplied by 7. Then there's this 2 multiplied by 7. Open the brackets here. 3 multiplied by 19 minus 6 multiplied by 7 minus 2 multiplied by 7. At this point, whenever they are like terms, we shall collect them together, which gives us 8 multiplied by 7. What did we want? We wanted a number which, when multiplied by 7, would give us 13. But we've just obtained a number which, when multiplied by 7, gives us 1. That's what we obtained. But what we want is a number which, on multiplied by 7, gives us 13. So that means we have to multiply this equation by 13. So multiply which equation? 1, 3 times 19 minus 8 times 7 by 13. Multiply that equation by 13. So when you do this, you then get 13 is equal to 39 multiplied by 19 minus, what is 13 times 8? And use a calculator even. Use a calculator. Math says that 13 times it was 13 times what? 13 times 8 is 104. So what do we have? Now what do we want? We want a number which, when multiplied by 7, gives us 13. What do we have? We have a number which, when multiplied by 7, gives us 13. That number is negative 104 mod 19. That number is negative 104 mod 19. So we ask ourselves, supposing 104 did not have a negative sign, how many times would 19 go there? Supposing 104 did not have a negative sign, how many times would 19 go there? 19 would go there 5.4. 5.4. So that means this same 19 can go into negative 104 negative 6 times. So that negative 6 multiplied by 19 will give me negative 114. I need to subtract. Negative 104 minus twice there, which gives me 10. It gives me 10. So that means x, this x, the same as 10 mod 19. The question wanted an integer. In fact, I should have written positive integer. That number is 10. 10. So you can try to prove that. Take 10 times 7, get 70, then divide by 19 and see whether the remainder will be 13 on division by 19. So 7 times 10 will be 70. Then when you divide it by 19, find out what the remainder is. And I can see from my calculator that remainder is 13. Again, let me erase so that I can show you the typed working. And of course, the answer is 10 there. I said, you see, this question here is open because the question has not told us a positive, least positive integer. So anybody will have given, even that, the one we got before dividing by 19, which was 104, I think, negative 104 could still be a result to this, this question, because the question is not specific on what it wants. It has not told us whether it wants a positive integer, or the least, or and so on. But it's always good manners to give the least positive integer. It's always good manners when you are doing this modular arithmetic. Give the least positive integer. Because if anybody was to do this question for uniformity purpose, everybody will be giving that least positive integer. So I'm just showing you the working, the typed working. And this one, I'm just doing the last one. The last one is here. You see, I found that this GCD was 13. Because it's me who was setting the question, I knew the GCD would be 13. And I also do it so that my GCD does not, so that I can say it has no solution. But if it's not you setting the question because you don't know the GCD, this is a very big number. You would first of all use the Euclidean algorithm. You would first of all use Euclidean algorithm to find the GCD. So what I'm saying is, you would ask yourself, how many times would 40, 43 go into this number? So 40, 43, how many times will it go into this number? Then find the remainder. Then ask yourself, what about how many times will this remainder go here? Go into 40, 43. So how many times will the remainder go there? Then find another remainder, and so on until you find that the GCD is 13. Then after that is now when you test whether 13 can divide 27. Because this is a small number, you cannot be knowing this GCD offhand. You cannot be knowing it. And I said for me, I did because I was setting. So I wanted to a number that would give me a GCD, two numbers that would give me GCD that would not divide this example. But for you, because you may not be having that GCD, you do it. And if you're using a program, we've already told you a program, find the GCD of A and B. And then you've told your GCD to test whether, your program to test whether that GCD of A and B can divide 27. The number here, you call it maybe C. So maybe you told it that you have this equation, B mod C, just write it here. You have this equation, AX is congruent to B mod C. Just tell your program that, and you are also telling a program to find out the GCD of A and B, and then test whether, let me call this GCD D, and then test whether D can divide C. And if D can divide C, then it progresses to solve the system. Thank you. That's where I wanted to end today's lesson.
Thank you, Dr. Sakwa. So I think unless there's questions, we can end it there. See you all tomorrow with 1-0. Then on Thursday for the in-person session. So have a good evening.